Hello, and welcome to IPv4 Network Design. We're all very familiar with IPv4. You've probably been working with it for years, and you may even have a pretty solid addressing plan in your network currently. In this video, we'll first do a brief overview of some more technical aspects of IPv4 addressing and subnetting, and then how to use those to design a repeatable plan that you can use within your network design. This is a plan that should be scalable and relatively easy to identify the purpose of the network in question. So, without further ado, let's jump right in. So the IPv4 address contains 32 bits of addressing space. And this is broken up into 4 octets of 8 bits each to simplify writing it out in dotted decimal notation. The address itself is comprised of a network identifier and host identifier within that network. So like the network is the street you live on and the host is the house number you live in. The thing that defines which portion of the address is the network identifier and which is for the host is the subnet mask. Moving from left to right, all parts of the mask which are ones indicate that respective bit in the address field is a bit which is part of the network identifier. So the first bit here corresponds to the first bit here, and the second bit to the second bit, so on and so forth, and all the ones here indicate the network portion, and then anything that's a 0 is the host portion. So the remaining zeros in the subnet mask indicate the respective bit in the address field as a member of the host identifier. And this makes sense once you realize that computers talk in binary, and that fundamentally that's what all the communication is in, right? So it receives this address that's 32 bits long, all being just a conglomeration of ones and zeros, and then receives a mask which has a certain number of ones in a row to indicate what part of that address is the network and what part is the host. Now, I mentioned dotted decimal notation already, but we didn't talk about CIDR, and it's pronounced CIDR, and it stands for Classless Interdomain Routing. And this notation expresses the subnet mask with a / and a number which corresponds to the number of ones in the subnet mask. And this is often referred to as the prefix length, because it's the length of ones in the network prefix. So the network portion here of your address is often referred to as the prefix. A lot of people, for simplicity's sake, go with the /24 network. Just on the bit boundary right here, end up getting 3 octets of ones and then 1 octet of zeros, and it allows for nice, easy, simple addressing. In the dotted decimal over here, you have this whole last octet here to go ahead and do host addressing. But sometimes we forget that it doesn't actually have to be this way. We can certainly do a /21 network instead, allowing 3 more bits for the host address, meaning now instead of just having 254 host addresses, we can have 2046. And it's when you consider the first address in the subnet is the network identifier, with all of the host bits being zeros, and the last address is the broadcast address for the network, with all of the host bits being ones. I wanted to take this chance to go over subnetting, and specifically how one determines the network identifier address for a subnet. Say you're given this address here, the 172.16.10.5/21, and you want to find what the network ID is. Well, you can do this one of two ways, really. The easiest, in my opinion, is to write it out in binary, which I've done right here. On top, we have the address, and below is the mask, which is 21 ones in a row. And here, you do a logical AND operation between them. And what that means is if both the subnet bit on the bottom here and the address bit on top are a 1, then the resulting bit down here is a 1. And if they differ, or are both zeros, then the resulting bit down here is a 0. And we find what this does is it gives us the same bits up to where the subnet mask turns to zeros. And the remaining bits are all zeros. Well, because if one of them's a 0, then the resultant is going to be a 0. So this ends up giving you the network portion of the address with all of the host bits being zeros, telling you what the network identifier is and where that network actually starts. So if you convert this into decimal, you end up getting 172.16.8.0/21. And honestly, I find this is really the best way to learn because it lets you really visualize what's happening with a subnet mask. Now, the second method is to determine what the stepping interval is of the networks. Here, in the third octet, we have 3 bits here for host identifiers. So we count the value places in binary. So 1, 2, 4, 8, up to where we get to the first 1 in the mask. So we know since that's where the first 1 is in the mask, the network IDs will step by 8s. So the first will be 172.16.0.0/21, and then 172.16.8.0/21, 172.16.16.0/21, so on, so forth. So hopefully you're aware of private addressing in IPv4, but I wanted to review what address spaces we have available to us in our designs. Of course, the reason private address spaces are called private and are reserved is because these address spaces do not uniquely identify a device on the internet, and therefore is not routable on the internet. We have 3 classes of networks in the private addressing space. Class A is a single large /8 network using the 10.0.0.0/8 space. Class B private networks are /12 networks, and the space which is used for Class B is 172.16.0.0 through 172.31.255.255, which contains 16 Class B networks. And finally, Class C networks, which we're most commonly familiar with, are /24 networks, and the space available is 192.168 through 192.168.255.255, which provides for 256 Class C networks. Now, this might feel a bit strange because we don't often deal with classful routing anymore. You can certainly subnet a Class B address space into a /24 using 172.16.0.0/24, for example, or make a smaller network if you don't need 254 host addresses available. We just want to be aware of the address space available for us to use in private addressing. Now, network address translation is the saving grace of IP version 4, and is the only reason, in my opinion, that IP version 4 is still around and that more people haven't migrated to IP version 6 yet. With network address translation, there's three main flavors: static NAT, dynamic NAT, and port address translation, which is also called NAT overload, or PAT. With static NAT, you're creating a static entry in the router or firewall, and the traffic is always translated the same way. The router does not keep track of the translated packet at all after it passes through. This is called stateless NAT, because it does not maintain a state table of the translations. It just has a single rule so that the traffic is always translated the same way. With dynamic NAT and PAT, the router keeps a table of what translations have occurred, so it can continue to provide consistent translation for the return traffic. Dynamic NAT is a one-to-one translation, where a single inside host computer is assigned a single outside IP address, and all traffic to and from that IP is translated to that host for the life of the table entry, which usually has an inactivity timeout to free up the IP eventually. And PAT, or NAT overload, is what we commonly use to provide internet access, which maps many inside source IP and port combinations to a single outside IP. I'll get to that a little more in just a moment, and it ends up adjusting the source port on the translated source to keep track of what return traffic goes to which inside host. It's pretty ingenious, if you ask me, and allows for tens of thousands of concurrent active connections, assuming your router can handle the traffic. And just as a note, in the upper right here with the terminology, I see this in Cisco's documentation, the inside local, inside global, outside local, outside global. I haven't seen this on a CCDA exam, though, but it wouldn't hurt to review briefly to stay aware of what these terms mean. And as far as NAT overload, just to give a little bit of a better sense here, say you've got your router and you've got your computer here, and you've got the internet and some other server that you're trying to access over here. So let's say your inside IP address here, that your address is 10.0.0.1. And let's say your public IP address here is 5.4.3.2. And when you go ahead and try and access this www server, this web server over here, let's say it's an HTTPS server. So you're sending traffic out, and it's going to have a destination port of 443. And the source port that your computer chooses is going to be some random number. Whatever your computer ends up choosing, it's usually very high. It might be something like, 64,112. Yeah. So that's the source. And the destination address is going to be this server over here. Let's just say it's Google 8.8.8.8. That's going to be your destination address for this packet that you end up sending, with the destination port of 443. So that ends up reaching your router, and it translates it through such that the source address on that packet is now 5.4.3.2. The destination address is still the same, the 8.8.8.8. Destination port is still the same, the 443, but the source port may not stay the same. It might if that port is available in the translation table on your router, but it might not if it's not available, and it might change that source. If it is available, then the router goes ahead and it's got, a table here where it ends up saying that source port 64112 ends up going to 10.0.0.1. Oops, 10.0.0.1. And so then it sends that off to the web server. Web server replies back to 64112 to this IP address. And then the router sees that 64112. It looks it up in its table. It sees that it's 10.0.0.1 was the IP address that this originated from. So it unnats this, undoes the translation to have the destination be your computer so that you end up receiving your traffic. And that's how NAT overload ends up working. Great. So now that we've done an overview of some of IP version 4's characteristics, we can get into the design recommendations. A first best practice to know and be aware of is that you should always separate your voice and data traffic into two separate VLANs. Nearly all businesses now are using voice over IP, and to allow for easier quality of service configuration and congestion monitoring, you should use a separate network for your voice traffic. Now, at some point, your addressing plan will blow up. If you keep growing, that is. There's only so much addressing space, and you can only conserve addresses so much without causing yourself all kinds of headache. I mean, just looking at the example addressing scheme here, you can see what happens if you go above 256 sites. If I have more than 256 buildings, maybe, then boop, I'm out of this 10 dot network. Or if I end up having more than 254 devices in my network and I have to go past this /24, so then my nice clean addressing scheme is just blown up and doesn't work anymore. I mean, your continuous addressing plan blows up and you start having to readdress or throw in non-continuous subnets or something like that. So that's why we want to generally split up our functions into different subnets as well, to reduce the likelihood that you'll be exceeding whatever your device limit is with that particular function. Now, one of the golden rules of address planning is to design with summarization in mind. As our business grows and you have your dynamic routing protocols distributing your routes, you don't want a wiring closet change to end up propagating through your entire enterprise. We summarize because that essentially sets the boundary for where routing updates stop for OSPF and where query messages stop for EIGRP. If you didn't end up planning your addressing scheme with summarization in mind, you might end up with a network that looks something like this. Now, of course, your enterprise doesn't need to be worldwide to end up with a large network, but you see how we have non-continuous networks coming out of the various countries here? And we end up sending a lot of different subnets up into our core. Now, of course, this happens, right? Where first you have a few offices in Asia, and then you branch out to Europe, and those offices get really big, so you make it a /21, but then Asia gets bigger, and you add a /22 there, and then you branch out into Americas, and so on and so forth. But you'll almost never come into a blank slate, or what's called a greenfield environment, and design a new addressing scheme. You'll have to do the best you can to plan for growth while designing this with summarization in mind. In this same example, if we had used contiguous networks throughout, we could make our routing nice and clean, just having these /18 networks going up into our core and advertised out from each area. It'll look nice. Your core routing table will be clean and concise and small, and it'll just feel good. Here, we even still have a lot of room for growth in each area. We haven't come close to using all of the addresses available in each /18, so you know we won't run into problems, at least not anytime soon. So, Cisco recommends for address planning to use role-based addressing, where you have 10.x.y, where x is the wiring closet number, the building number, floor number, etc. Just x is the location identifier, and y is the function of the VLAN at that location. This allows for not only summarization of each location into the distribution and core, but also easy identification of what an address is used for. You can use VLAN 10 for data, 11 for voice, 12 for printers, 13 for Wi-Fi, so on, so forth. Your Excel sheet you made of your address plan will be clean and tidy and very readable and easier to understand. This feels simple, but also, as you can see, it's also likely this will end up with some address wastage. The way to minimize that is to go about a more difficult method of addressing called bit splitting. This really comes into place when you're using subnets that don't end at the bit boundary. So using something smaller than a /24 usually. The best way to organize this in your spreadsheet is really by binary. You can have the dotted decimal equivalent in a column, but in another column, to have the network line up well and understand which network corresponds to what function easily, you can list the binary equivalent of the network portion. It might be more tedious, but you'll end up with much tighter subnets and less address wastage. Just make sure you plan appropriately, of course, to ensure your plan won't blow up on you when you start needing more devices on the network than you have addresses available. So in the last slide here, I wanted to do a brief case study to bring this all together in a more real-world example. Let's consider the Apple Store, right? Here's how I would design their network. So I did reverse Cisco's addressing plan a bit, but I'll show you why. First, the data VLAN is for their internal devices, like the Genius Bar computers, the point-of-sale systems, the automatic screen repair machines, and perhaps the security devices and cameras as well. And that's our VLAN 10 here. Of course, they use voice over IP, and we'll need a separate VLAN for that. So we have that here as VLAN 20. And then the internal Wi-Fi for the handheld iPhones and the stuff that they use to check out, and for the staff devices too, for them to connect. And I like to create a separate VLAN for servers and printers here, VLAN 40. And it would also have the point-of-sale servers, the security system, and printers for the repair shop and the back office, etc. And the exit VLAN is just a little point-to-point, something that goes from your router to your multi-layer switch, just to get traffic out into the network or into the internet, and this never needs to see the light of day, or needs to be able to be addressed from anywhere else in the enterprise except in the store there. And the same goes for the public Wi-Fi. Now, this subnet is so huge, a /22 here, because one, we can, and two, because Apple has these huge product launches, right? Where hundreds or thousands of people are waiting outside to get the new iPhone, and they all have their existing phones and want to connect to the Wi-Fi. Then, finally, of course, we have the management VLAN, just naturally. Now, the reason why I started at 0 up here for VLAN 10 instead of VLAN 1 or VLAN 10 is because these 4 VLANs here are the ones that need to be routable across the enterprise. So we can take these 4 and summarize them into 10.0.0.0/14 and say that's the eastern half of the United States, right? Let's say we've got United States. Okay, close enough. Say that's the eastern half of the United States, 10.0.0/14. Then say you've got 10.4.0.0/14. And then that's your Midwest section where you've got, all of these stores, all the Apple stores sitting around here in the East and the Midwest. Then your next region here in somewhat West, you've got your 10.8.0.0/14. You see where I'm going here? Planning big so that you can summarize your regions here, and then you end up having some central data center or couple of data centers where these summaries end up going into and being summarized out to each other, because these usually all need to talk to each other, or talk to other locations, or talk to the servers in each of these data centers and be able to fail over to them. And this allows for less address wastage and more growth along with summarization. So I thought this might be fun, and thanks for sticking with me. And just like our previous sections, let's drop into a couple of practice questions. For a VLAN that requires 60 hosts, which subnet is most efficient? Is it A, a /26, B, a /24, C, a /20, or D, a /27? Well, pretty immediately, we know that a /24 has 256 addresses in it and allows for 254 hosts. So that seems way too big. That's almost certainly not the answer here. /20 here, that's even bigger. So we know that that's not going to be the answer. So a /27, let's take that here. That a /24 is that we have 8 zeros here for our host addressing, and that's what gives us 254 addresses. Now, if we take 3 of those and make those 1s, then we end up having 5 zeros left here. So then this would end up giving us, that's 2, 4, 8, 16, 32. So this would give us 30 usable addresses. That's just not enough. But then if we add one more bit here, we double the number of addresses we have. So then that's 64 minus 2, of course, for the broadcast and host and network identifier. So that's 62 usable addresses in a /26. We know that that is our answer here, A. Which IPv4 addressing technique can be used with proper address planning to reduce the number of entries in a routing table? Is it translation, filtering, summarization, or tunneling? Well, translation doesn't really have anything to do with routing. Filtering, you can filter routes, but the answer here should be pretty obvious, that it is C, summarization. Now, I hope this has been informative for you, and I would like to thank you for viewing.